Hello everyone, in this Thierry Sicard tutorial number 43 we will talk about Russel Ohl working in the Bell Labs of AT&T, which got the intuition that semiconductor more or less resistant was due to impurities. This brings to the idea to get the semiconductor as pure as possible, then to dope the semiconductor with specific element to get semiconductor doped P or N. At room temperature, ultra-pure silicon has one free electron over more than 3000 billion of atoms, so the pure silicon does not conduct electricity. In 1833, when Michael Faraday noticed that silver sulfide resistivity decreases when temperature increases, of course the silver sulfide had a lot of impurities, like the galena crystal used by Brown in 1874. At that time, nobody knows that the conductivity was due to the impurity in the semiconductor material. And even in 1839, the germanium used in the Bell Labs solid-state team was not ultra-pure. At the time, almost no one knew anything about the impurities within these crystals. But Russel Ohl found that it was the impurities which made some sections more resistant to electrical flow than others, and thus it was the barrier between this area of different impurities that made the crystal work. Later, he discovered that super purifying germanium was the key to making repeatable and usable semiconductor material for diodes. Russel Ohl found that the crystal should be as pure as possible up to 99.99999999%, means 9 number after the dot. With an ultra-pure semiconductor material with almost no impurities, we will be able to control those impurities with what we exactly want to become N and P doping. For the P doping, we will take element on the third column of the periodic table as the boron, which has only 3 electrons on its external shell. Those 3 electrons will be used for the covalent link, but 1 electron will be missing, creating a low energy position for an electron in the covalence band. For the N doping, we will take element on the 5th column as phosphorus or arsenic, which have 5 electrons on their external electron shell. 4 electrons will be used for the covalent link. The 5th one will be free. I give 3 examples of N doping concentration. We can get several decades to go from 1 free electron for 10 atoms, which is very high doped, to 1 free electron for 10 millions of atoms, which is very light doped. In this slide, we will see the N-doped silicon with a phosphorus element. On the top left, we can see the phosphorus atom in green with 2 and 8 electrons on its first 2 shells and 5 electrons on its external shell. Inside the silicon crystal in 3 dimensions, we can see a silicon atom with 2, 8 and 4 electrons on the external shell with its 4 covalent links. If one silicon atom is replaced by a phosphorus atom in the crystal, on the 5 electrons, 4 electrons will be used for the 4 covalent links, and the 5th one cannot participate to the covalent link, so it is free and can move in the crystal and participate to the electric current in the conduction band energy. To be able to do a very accurate doping, the silicon crystal must be as pure as possible. Some doping examples are given from 1 atom for 10 silicon atoms down to 1 atom for 10 million silicon atoms. We can consider that each N-doping atom releases a free electron, so we take an insulator material as ultra-pure silicon and we control the N conductivity with the density of N doping atoms. All those free electrons in a crystal can be seen as gas molecules in a volume, following the same perfect gas law PV equal nRT. For an n-doped semiconductor, electrons are the majority carrier, so the equivalent electron pressure in comparison with a gas is much higher than the p-type doped. In this slide, we will see the p-doped silicon with the boron element. On the top left, we can see the boron atom in pink with 2 and 3 electrons on its external shell. If one silicon atom is replaced by a boron atom in the crystal, the 3 electrons will be used for 3 covalent links, but the 4th covalent link will miss 1 electron. This lack of electron is called hole. The hole can be seen as a low energy position in the valence band. As it is a low energy, if a free electron is close to the hole, it will take the low energy position. We can consider that each p-doping atom releases a hole, so we take an insulator material as ultra-pure silicon and we control the p conductivity with the density of p-doping atoms. All free holes in a crystal can be seen as gas molecules in a volume and following the same perfect gas law PV equal nRT. For the p-doped semiconductor, holes are the majority carrier, so the equivalent hole pressure in comparison with the gas is much higher than the n-type doped. Following this three-dimensional crystal representation for p and n doping, we will have a look on the Fermi-Dirac distribution. The Fermi-Dirac distribution gives the probability that at thermodynamic equilibrium, a state having an energy E is occupied by an electron. In this slide, all the plots are done at 300 Kelvin. The energy E is in electron volt, so delta E minus EI can be replaced by QV, where Q is the electron charge. Then KT over Q is replaced by the thermal voltage VT. At 300 K, the thermal voltage is close to 25 millivolt. E minus EI divided by KT is replaced by V over VT, and if V over VT is replaced by X, we can plot the curve 1 over 1 plus exponential X. For E minus EI equals 0.5 electron volt, X equals 20. Now, if we zoom in the right rectangle, the curves comparison 1 over 1 plus exponential X and exponential minus X shows that when X is bigger than 3, both curves are equal. This means that in the conduction and valence band with X greater than 20, the function can be replaced by exponential minus V over Vt. If we want to visualize the intrinsic concentration Ni with a small right triangle, of course the Fermi-Dirac distribution shape in the band gap is not correct. N electron equal Ni in the valence band and P hole in the covalent band. The Pn product is always equal to Ni square. At 0 degree Kelvin, 100% of the electrons are in the valence band and 0% in the conduction band. At 300 Kelvin, you can see the probability to find electron at E equal EC is close to 0, and at 0.1 electron volt over EV, it is close to 1. With 5 10 to the power of 22 atoms by centimeter cube for the silicon, and 1.45 10 to the power of 10 free electrons by centimeter cube for the intrinsic concentration Ni, we will get 1 free electron in the conduction band for 3.4 10 to the power of 12 atoms. If we increase the temperature to 500 degree K, which means close to 200 degrees C, the probability to find electrons in the conduction band increases. To see the variation, I've wrote 0 and 9 in red to visualize the probability variation versus temperature. The probability to find electrons in the conduction band at 500 K is 112 times more than at 300 K. Here we will compare the energy band occupation between intrinsic and n-doped silicon. As the intrinsic concentration Ni is proportional to the cube of absolute temperature T, at 0 K, Ni equals 0, which means N equal P equal Ni equals 0. To do a visual animation of the electron and hole variation between intrinsic and doped silicon, I set arbitrary Ni equal N equal P equal 5 in an intrinsic silicon, so you can see 5 electrons in the conduction band and 5 holes in the valence band. The rule Np equal Ni square gives Ni square equal 25. Even at room temperature, the intrinsic pure silicon is an insulator. Now we set donor atom Nd at 25 atoms by centimeter cube. All donor atoms release their free electron, so N equal Nd equal 25. The Fermi level will move close to the EC energy of the conduction band, but to keep the rule Np equal Ni square, some free electron of the donor atom Nd will move at the lower energy position in the valence band to keep just one hole, so P equal 1 and Np equal 25. Here we will compare the energy band occupation between intrinsic and p-doped silicon. To do a visual animation of the electron and hole variation between intrinsic and doped silicon, I set arbitrary Ni equal N equal P equal 5 in an intrinsic silicon, so you can see 5 electrons in the conduction band and 5 holes in the valence band. The rule Np equal Ni square gives Ni square equal 25. Now we set acceptor atom, Na, at 25 atoms by centimeter cube. All acceptor atoms provide hole, so P equal Na equal 25. The Fermi level will move close to the EV energy of the valence band, but to keep the rule Np equal Ni square, some free electron in the conduction band will move at the lower energy position in the valence band to keep just one electron in the conduction band, so N equal 1 and Np equal 25. I want to thank you for your attention. On my next Thierry Sicard tutorial number 44, we will talk about what happens if a n-doped and p-doped silicon are close to each other, building a p-n junction. So see you soon and stay tuned.